Hi, I'm Majeed. I'm a master's student at University of Maryland's Human-Computer Interaction Lab, and today I will be talking about MakerWear, a tangible, wearable construction kit for young children. Wearable construction kits, such as LilyPad or Arduino, have shown promise in attracting underrepresented groups to STEM, expanding perceptions of computing and empowering users to create self-expressive and personally meaningful computational designs. These kits, however, require programming and understanding of circuits and manual craft skills like sewing and soldering. Though this complexity allows users to create diverse and increasingly sophisticated designs, but it also presents significant challenges to young children. Indeed, the vast majority of the literature on e-textiles as a learning platform for computational design has been with older users and most often high school students. That's why, in our work, we are trying to enable young children to design and build their own interactive wearables. What do children want to build, and how can we support these goals? How does working with our tools impact skill development and perceptions of STEM? To address these questions, we employed a 2-year iterative design process that included 5 participatory design sessions with young children, 2 design probe sessions with STEM educators, and lab and museum-based pilot studies with our increasingly refined prototypes, and deployment studies of our final prototype in single and multi-session workshops. For our participatory design sessions, we employed a method called Cooperative Inquiry, in which an intergenerational group of children and adults work closely together in order to brainstorm, design, and test technology for children. In early sessions, children used prototyping material, such as foams and cardboards and markers, in order to help us understand what wearable behaviors they would like to build on their clothes. In later sessions, children helped us by testing initial functional prototypes and design activities. We also solicited feedback from 2 groups of professional STEM educators that provided design ideas such as improving MakerWear's support for lo-fi material integration. From these sessions, several recurring themes emerged, such as allowing children to build wearables that are reactive to their body and its physiology, to support for social interaction, and to be responsive to the changing environment. We were also inspired by digital physical construction kits that include a set of snappable modules that work instantly as they're connected together, which allows for rapid prototyping and a highly iterative design process. Informed by our participatory design sessions, as well as literature in developmental psychology and past work in programming toolkits for children, we made the current MakerWear system, which is open source. MakerWear is comprised of 2 parts: single-function plug-and-play magnetic modules that can be combined to create complex interactive behavior, a flexible magnetic socket mesh that is pre-sewn into clothing that provides an easy method to attach and remove modules. MakerWear uses a tangible programming approach. We design each module to have 1 input and 3 outputs. When a module receives an input, it is processed and transformed into a new signal that is forwarded to all 3 outputs. This allows for creations to easily extend and branch into nonlinear forms. We have currently designed 5 different types of modules: power modules, which provide power to all connected modules; sensors that sense and translate physical phenomena into analog signals; modifiers that transform signals from one type to another; actions that translate analog signals into perceptual forms; and a number of miscellaneous modules. We've currently designed 36 different modules, including 12 sensors, such as motion, heartbeat, and temperature; 12 actions, including LEDs, motors, and sound; 7 modifiers, including an inverter or a potentiometer, which we call it a volume knob because it's easier for children to understand; 4 miscellaneous modules; and finally, power. Another way to organize these modules is by their theme. When we were designing MakerWear, we focused on building modules that would allow children to leverage the unique opportunities of wearability, particularly movement, the body movement and its physiology, the changing environment, and communication. Each module is custom built and contains 4 different layers. The top layer exposes the key electronic component to that module, in this case, an infrared thermometer. The second layer is the module cover, which is laser cut in our lab with a child-friendly name and icon. The third and fourth layers are made of custom PCBs. The third layer includes an embedded microcontroller, while the fourth layer includes a strong magnet and special contact springs to ensure a strong connection to the socket. The socket mesh serves 2 primary functions. First, an easy and robust mechanism to attach and detach modules to clothes. It also provides power, ground, and input-output connections to adjacent modules. We've currently designed 2 different types of socket meshes. Those that are sewn into clothes, like the one that I'm currently wearing, and those that are self-contained fabric patches that could be attached to different kinds of clothes and artifacts, such as backpacks, using safety pins. Now let's actually make some designs using MakerWear. All designs in MakerWear start with a power module. The simplest functional program is this: power in action. In this case, the light will always be on. In order to make the design interactive, we need to add a sensor. So in this case, let's add a motion detector. And that's how we can create motion reactive clothes, similar to light-up shoes. Notice the fade effect on the light-up shoe. We can actually add this behavior to our design using a fade modifier. We can then add a bunch of other kinds of action modules, such as sound makers, spinners, vibration, and other kinds of lights that will all respond to the wearer's movement. And because each module has 3 outputs, it allows for designs to be rearranged in different orientations to create functionally equivalent designs, such as this one or this one. We can create a diverse set of designs tangibly simply by placing modules, such as this auto headlamp hat that will automatically light up when it's dark, or this chameleon clothes that will change color based on the color of nearby objects, or this laser tag armband, which includes 2 parts. The first part shoots an infrared laser beam whenever the button is pressed, and the other side will turn red whenever it's hit by an infrared beam. Now let's actually make this design. Whoops. Oh, technical issue? No sound. Let me just... Sorry about that. Okay, there we go. So whenever the button is pressed, the blue light will turn on, then the sender will emit an infrared laser beam. And on the vest, the receiver will receive the infrared beam and will turn on the red light accordingly. So as children gain more experience, they're able to build more complex designs. So what if children wanted to count the number of times that they were tagged? As you can see, children are able to make this design simply by placing a counter and a number module. Or what if children wanted to build an end game condition for their design so that it would sound an alarm whenever they were tagged 5 times? So using a threshold module, which is set to 50%, they are able to activate the alarm whenever the number passes the threshold. To evaluate MakerWear, we used a workshop-based study methodology. A total of 32 children participated, with 16 female with an average age of 8 years old. We conducted 2 single-session workshops and 3 four-session workshops. Children were grouped into sessions based on their age. The youngest group had an average age of 6 years old, while the oldest was 10. In terms of technology use, most children use a computer at least a few times a week, and around half of the children reported that they've used a graphical programming system or an electronic kit at least once. The workshop sessions lasted just over 1.5 hours, starting with a pre-study questionnaire, a brief introduction to MakerWear, and a 70-minute block of building and playing with MakerWear, along with design challenges, and finally a post-study questionnaire. The multi-session workshops followed a similar format, but with more content. Notice that on day 3 and 4, children worked on their own designs towards a final project in which they presented to their friends and family during a final exhibit. To analyze children's use of MakerWear and their computational thinking skills, we used a mixed methods approach, including session video, design challenge performances, and user creations, artifact-based interviews, and pre- and post-study questionnaires. In terms of findings, overall, children were highly engaged in the making experience. They were able to successfully build a wide variety of designs and learned and actively applied computational thinking skills. Now I'll go over 2 of the findings specifically. So, for example, to assess children's understanding of input, output, and sequencing, we asked children to fix a number of designs. So when given a design that had an input-output error, children had to flip the light around so that it would receive the sensor's output. Or when given a design that had a sequencing problem, they had to make sure that the sensor would come before the action module in order to have an effect. From these fixed design challenges, we learned that children generally understood the concepts of input, output, and sequencing. On the post-study questionnaires, when we asked children to compare designs with and without branching, the older children seemed to understand the concept, while the younger children struggled on the questionnaire. However, we later noticed that they are actually using multiple outputs of a module or branching in their constructions that they make. We also noticed that children's understanding of different concepts improved over time. So, for example, on questions related to sequencing, their scores went up from 47% to 77%. And similarly, on questions and designs related to conditional logic, which was only asked from the 2 older groups, their scores went up from 20% to 78%. The final projects provides insight about what wearables children can create. And for an analysis, we focused on how children use modules in their designs, the technical complexity, and what they built. We quantitatively analyzed their children's final projects and found out that as age increases, not only children use more modules in their designs, but also more complex modules like sensors and modifiers with increasingly sophisticated structures. However, that was not the case for using lo-fi materials, in which it was used the least by the oldest group. Children were able to build designs that were personally meaningful to them. The most common theme was sports and fitness, followed by role play, sociodramatic play, and a number of other miscellaneous projects. I will describe a few examples in a moment. In terms of sensors used, the most commonly built designs sensed movement, followed by manual input like pressing a button, and the environment, the physiology, and social interaction. Now I will highlight a few of the projects that children made. Starting with role play, Omar, age 6, built a wrecking ball armband.
That whole thing. Let's do something with that.
Omar's design used the button in order to activate lights and sound, as well as to turn a rotator that had ping pong balls and pipe cleaners attached to it. For sociodramatic play, Austin, age 9, made a magic Pokemon doll that was controlled from his vest.
So whenever I'm pointing the sender at the receiver, and I do something to activate something on this one, it sends it to this one and activates something else.
Austin's design used 2 different socket meshes, one on his Pokemon doll and one on his vest. He used an infrared sender and receiver, as well as a wave generator that would as well as a wave generator on the doll that would flash lights and sound whenever it received a message from the vest. For fitness, the most common theme, Sarah brought her own lacrosse stick from home and made a smart lacrosse stick.
So if I'm cradling the stick and she comes up to try to check me, the distance sensor will notice if she's there, which means I can run away.
Notice how she attached a fabric patch to her lacrosse stick to build a platform for making her design that used distance sensors, sounds, and lights. And finally, Emilia made one of the most complex designs. She made the next generation running clothes.
I made a bunch of clothes that you can wear if you're jogging at night. When it's dark and you're moving, a bunch of lights turn on and vibration.
Ready, start running.
It's like a little fan that's counting the beats.
I really love the creativity in her design and how she used 4 different socket meshes and over 40 modules. I want to point out 2 key points in her design. She was one of the only children that cascaded multiple sensors in order to create an implicit "and" condition. So in order for her clothes to light up, it had to be both dark and she had to be running. And she also created a fairly sophisticated heartbeat tracker that would beep and light up with every heartbeat and counted her heartbeats up to 99. Notice how she cascaded 2 counter modules to support multiple digits. And moving into future work, in terms of MakerWear's form factor, we would like to make modules that are thinner and more flexible. We are also planning on enabling older and more experienced children to program their wearables with a graphical programming interface. And finally, we are interested in enabling children to program complex behaviors and gestures using interactive machine learning. In conclusion, MakerWear is a tangible, modular approach to wearable design that allows children to create a wide variety of wearables and actively apply computational thinking. And finally, children were able to build artifacts that they were proud of. In closing, I would like to recognize our team and partners who enabled us to do the work that we do. And with that, I would like to take any questions. Thanks.
Can John and Liang come up, please, quickly? So this last paper actually got a Best Paper Award, which means it was in the top 1% of all the accepted submissions. Oh, you guys are all here. Yeah, so huge round of applause. There you go. Congratulations. And now it is lunchtime, but if you have any questions, please ask questions, because obviously best paper, so you guys should have like tons of things to question him on.
Got a question? Oh. Yeah, go for it.
I was actually curious why you call it MakerWear and not something like ProgramWear or CompuWear or something like that, because I was expecting to hear some sort of discussion about maker identities or making, but that wasn't necessarily.
Well, thanks for that question. It is definitely about programming. It is about all the things that you say, but we wanted to focus on the making part of MakerWear so that it's both about making and wearability. I guess we couldn't make the name too large.
Hey, Daniel Ashbrook from the Rochester Institute of Technology. I'm curious if you have thought about a kind of end game for this to make it permanent.
To make it?
To make it more permanent. So, now I've made my augmented running clothes, but if I knock into it, maybe the modules will fall off. So now I want to make it into something that is a finished product.
I see. That's a great question. First of all, I have to point out that we never saw in our workshops that a module would like throw off or something. But in order to make, and we actually wanted to make the design of the building process of MakerWear to be a highly iterative process. So that's why we wanted to do that. But I believe that yes, there should definitely be a permanent solution to that. I mean, if people yeah. Did I answer your question?
I think like part of it is the hope is they would learn through this and then maybe gain experience or confidence in transition over to LilyPad or Adafruit
Yeah.
or some other platform.
Yes, I guess part of my thinking is there a path to go from this to the next thing?
Yeah, I mean, it's interesting to think about the schisms that might exist
Yeah.
there. I mean, I think the complementary, he mentioned it, this like tablet interface that we're working on now, and he actually has a working demo of that.
Cool.
Might be a better scaffold to the traditional microcontroller platforms like LilyPad, but it's a great question to study for future.
Yeah. Really nice, thanks.
Thanks.
Hi, my name is Stefania Druga. I'm from Lifelong Kindergarten Group at Media Lab, and I very much appreciate your project and the fact that you made it open source. I wanted to ask you a bit more about the computational thinking framework, and why did you decide to go towards a block interface for coding? What were the things that you felt they couldn't learn by programming physically with the blocks? And how do you envision the creations will change when the kids will be able to also use these digital interfaces to program their creations? Thanks.
Sorry, I didn't understand the last part of your question.
How do you think the projects will change, maybe in terms of complexity or diversity?
There are children's projects.
Yeah.
So first of all, in terms of, the first part of your question was about
computational thinking.
Yeah, computational thinking. So and tangible blocks. So yeah, I believe that there has been proven research that shows that working with tangible blocks is more intuitive. So that's why for younger children it seems to be a very good choice because it's easier to grasp and children are it's part of the developmental psychology theory. And regarding so that's why we chose it to be a tangible construction kit. And regarding to the second part of your question, which was
how the projects will change when they will be able to program them with blocks on a digital interface instead of only program them physically.
So yeah, I think that definitely the complexity of their designs will change as they will gain more experience. So let's say if they wanted to build a fitness tracker and they could use a graphical programming interface and other kinds of stuff, they can build a whole Fitbit, for example, for themselves. Yeah, we would see something like that to happen.
The second part of that really that we're really interested in exploring is transparency. So there's a lot of things that are sort of abstracted away here that we think the visual programming language might be able to elevate. So just like how the system is sort of working, some debugging support, and some other things that are important to computation.
And the representational model, right, of the logic. Yeah. Thanks.
Okay, so because I know everyone is super excited to go get lunch, I'm going to stop the questions. I'm sorry, Majeed is very excited to answer your questions, so come find him later. The next sessions begin in the afternoon.